Hello and welcome to your matter and measurement flip video. Matter is something that should have been defined for you in your other science classes, so most of what you're going to hear here is going to be a little bit of a review, but we will start looking at how we actually depict different samples of matter using something called particle diagrams, which are very important in chemistry. Matter is defined as anything that has mass and takes up space. This definition kind of always seemed a little bit strange for me because I was like, well, isn't that everything? What matter doesn't include are things like energy, so electromagnetic radiation, such as radio waves, visible light, things like that. But matter is anything that we can pick up and hold, we can mass or weigh. We can also matter can also have charges, which is really important. So it's basically the stuff that makes up our world. There are two major categories of matter. There are what we call substances and mixtures. Now, the word substance, I find because we use it very differently in how we speak in day-to-day language, can be a little bit confusing for some students. For example, if you were to drink a glass of Kool-Aid, you're not drinking a substance. You're drinking a mixture. If you were to put some salad dressing on a salad, you are not putting a substance on your salad, you're putting a mixture on your salad. So this is an important distinction that we begin to make when we get into chemistry. So there are two things that we classify as substances: elements and compounds. There are two types of mixtures that we generally talk about: heterogeneous and homogeneous. So to break these down a little bit, first type of substance that we talked about, the very kind of simplest type of substance, is what's called an element. And this is a substance that consists of only one type of atom. What I mean specifically by one type of atom is that all of the atoms in that sample have the same number of protons. I'm actually going to draw you two examples, even though I only have one example space. So one example that you might talk about is iron. Okay, what the heck? Let's talk about some iron. Now, iron's a solid, so iron particles might be kind of close together like that. I'm going to move this over just a little bit. We could also talk about certain other types of elements that actually exist bonded together. So you've seen oxygen written as O2 before. So oxygen is actually two oxygens stuck together. That's still an element, because both of those oxygens, if you go to the periodic table, you look up oxygen, it's always got 8 protons. And those iron atoms that I drew on there, each of those has 26 protons. So they're the same because they have the same number of protons. A compound has to have atoms in it that contain different numbers of protons, but how they're combined is actually very important. So a compound is a substance that is made of 2 or more types of atoms, in other words, 2 or more elements, combined in a fixed ratio. And it has its own unique properties. And I'm going to break down this definition a little bit because there's a lot going on there. Great example I'd love to talk about is water. So you've, had access to water your whole life. You've experienced it a lot. I talk about it a lot in chemistry. What you know about water, you probably already know it's H2O. So it's actually one oxygen. It kind of looks like a little bit of a Mickey Mouse. So if we were going to draw a sample of some water molecules, what you're going to notice about these, and sorry, my art's not really amazing, but what you're going to notice about these two molecules of water is that each of them contains one oxygen, which has 8 protons in it, and 2 hydrogens, which each contain 1 proton. So we have atoms with different numbers of protons, but they are combined in a fixed ratio of 2 to 1. If we change that ratio, we actually change the identity of the compound. Also, what's important to note here is water has different properties than oxygen and hydrogen. Oxygen and hydrogen would be gases at room temperature. By combining them into water, they're now a liquid at room temperature. These follow the law of constant composition, which says all samples will have the same ratio of elements within a compound. Every sample of water, whether you take the amount of water in the ocean or the amount of water that's in a cup of water or 1 milliliter of water, you will always have a fixed ratio of 2 hydrogens to 1 oxygen. And you can look at that in the mass of those elements as well. Mixtures are a little bit different because they are a physical combination of 2 or more substances. And mixtures can contain either elements or compounds. So you can actually have a mixture of 2 elements that just aren't bonded together. You can have a mixture of 2 compounds. You can have a mixture of 4 compounds. You can have a mixture of 1 element and 3 compounds, 3 elements and 1 compound. You have all sorts of different combinations there. These can be separated by physical means. And a great example to talk about is salt water. I like this example because I think water is something you're very familiar with already, and most of you have had some experience with salt water, and whether you dissolve salt in water or gone to the beach. So water molecules look like this. Now, the way that I'm going to depict salt water right now is not completely accurate. We'll make this picture a little bit more accurate later in the year. But what I do want to show you is we have the water in here, so that's one substance. What makes this a mixture is I'm now going to put something different with it. And salt water actually has like kind of a special way that it lays itself out that does not really look like what I have up here. But what's important about this picture is this. We have 2 different substances in it. So we have one substance that's a blue and a red. We have one substance that's water, the oxygen with 2 hydrogen. They are physically combined. They are not chemically bonded to each other in this picture. So therefore, this is a mixture. A little bit more about mixtures. Remember, this is 2 or more substances physically combined. Some specific stuff that's important. Sorry, I had to pause there for a second. Components that retain their original properties. So when you make salt water, it tastes like salt and water. When you actually talk about salt itself, it's sodium combined with chlorine. Regular elemental sodium actually will catch on fire in water. You can put salt in the water without having any issue of that. Sorry, I got interrupted again. Anyway, so components are going to retain their original properties. In a compound that is not the case, as I mentioned, regular elemental sodium will catch on fire in water, but because sodium is bonded with chlorine and salt, no longer has that same reactivity. So you put salt in the water all the time, no big deal. However, when you taste salt water, you really taste that salt in there. Mixtures can have their components separated by physical means. So one thing that we see all the time around here in the winter is we put salt on the sidewalk, and then when the water kind of dries up, you see that white crusty salt left behind. So by evaporating away water, we can separate salt from water. And the proportions of the components may vary. So we mentioned in a compound like water, we have to have a ratio of 2 hydrogens for every 1 oxygen. You can vary your components in a mixture. For example, if you're making Kool-Aid, you can put in lots of Kool-Aid mix and make it really strong, or not as much and make it really weak. So you can vary the ratios of those components. I just like to wrap up a little definition for you guys about heterogeneous and homogeneous mixtures. This has to do with particle distribution. We deal mostly with homogeneous mixtures in chemistry. Homogeneous mixtures are when we have samples that are the same all the way out. If I make a saltwater sample and give some to everyone in the room, the samples are all going to be identical. So saltwater, or what we call solutions, which we'll talk more about, are examples of homogeneous mixtures. Heterogeneous mixtures do not have uniform distribution. I love to use salad dressing for this one, especially those ones you have to shake up. Chicken noodle soup, soil, anything where if you take different samples out of that mixture, they may be a little bit different from one another because of the particle distribution varies. So a little summary for you. Elements cannot be broken down by physical or chemical means. Compounds can be broken down by doing a chemical reaction, breaking of bonds, And mixtures can be broken by mixtures can be broken down or separated by physical changes, such as boiling away water, using filtration. We'll talk more about those a little bit later on. Elements and compounds, because they are substances, they have a very fixed, what we call constant composition. They are the same all the way through. So an element only has one type of atom in it. Compounds, you're going to have that fixed ratio of every group having one oxygen to two hydrogens. In a mixture, you have some more variability there. Elements are made up of atoms with the same number of protons. In order to have a compound, you have to have at least two different elements that are chemically combined. So those chemically combined atoms will have different numbers of protons in them. And in order to have a mixture, you have to have two substances that are not bonded together, but are physically combined. A little bit of some definitional stuff about mixtures, and we get into mixtures a little bit more down the road. So we mentioned that solutions are an example of a homogeneous mixture. Some words to know, the solvent is what your dissolving medium is. Frequently in chemistry, this is going to be water. Our solute is what gets dissolved. So if we're talking about salt water, for example, our solute would be the salt. Or solvent would be water. You can have gaseous solutes, things like that. We'll talk about that a little bit later on. Most of our mixtures in Regents chemistry and honors chemistry are going to be aqueous solutions, which are homogeneous mixtures where water is our solvent. And we have a little symbol for this, which is AQ. So if I wanted to tell someone that I have a saltwater solution, I can actually write NaCl for salt, follow it with a little AQ, and people know I'm talking about a homogeneous mixture where I have salt dissolved in water. Couple of important definitions that you've probably used these terms. I just want to clarify them a little bit. Atoms are kind of those smallest building blocks of matter. So atoms are smallest individual particles that retain the properties of that particular element. Parts of an atom are the proton, neutron, and electron, which we'll be talking a little bit more about later. And for our purposes, they cannot be broken down. Are there things that can happen where protons and electrons can kind of do some moving around? Yes, but for our purposes, we say atoms cannot be broken down because it's not something we can just easily do. Molecules are multiple atoms that are chemically linked together. And these can be broken down by doing a chemical reaction. So whenever we talk about actual chemistry happening, breaking and forming of bonds, that's when we're talking about breaking down a molecule. Now, an important distinction to have: you can have atoms of elements, you cannot have atoms of compounds, because atoms are only one thing. However, you'll notice in the second part of this chart, you can have a molecule of an element. So this is still an element right here because these are both oxygen, but it is a molecule because there's two oxygens stuck together. Compounds also always exist as molecules. You may want to pause the video for a moment to write these down. So the big difference between these is whether or not they are chemically bonded. Atoms are the very smallest unit of an element, so they're always single. And in a molecule, you have to have at least two atoms that are chemically bonded together. So one of the things that we're going to be working on doing is identifying samples of matter. So we're going to wrap up with looking at a couple of these pictures. If we want to have a mixture, we have to have two different substances. So when you look at picture one, if you look at the individual groupings in here, they're all the same. That is indicative of a substance. If you look at picture number two, this group and this group are different from each other. They are not attached. So that is a mixture. It's a mixture of two elements. In pictures 3 and 4, they're pretty simple to look at. You can very clearly see all of these groups are the same as each other. That's going to be a substance. All of these groups are the same as each other. That's going to be a substance. So only choice 2 is a mixture. Question number 2 is looking for us to identify pure substances, and these are really the same pictures. So picture, or choice 2, we identified as a mixture up above because those groupings are different. Choice 1 is a substance, it's just a compound. Choice 3 is a substance, also a compound. And choice 4 is a substance as well. Or 3 is an element. I said compound. So this is an element, this is an element, and this one right here is a compound. So that identity is pretty important, but they're all examples of substances. Which of the following particle diagrams represents a mixture of one compound and one element? So it's a little bit more specific. Choice 1, this is a compound, this is a compound. It is a mixture, but it's a mixture of two compounds. Choice 2, this is an element, this is a compound. So that's our answer choice. Choice 3 is also a mixture, element, element. This is a mixture of two elements. And choice 4, we're going to have a particle diagram that represents a diatomic element. Di means two, so this is a two-atom element. That's like when you're talking about things like O2 and N2. We will talk more about those going forward. Choice 1 is obviously a compound, two different things stuck together. Choice 2 would be a two-atom element. So you have two atoms that are the same stuck together. Choice 3 is actually a mixture of two diatomic elements. So it's a little bit of a teaser on this one. Yes, there's diatomics there. However, there's two of them, so they are a mixture.